Okay, let's go ahead and get started. We've got places to go, people to see. Evalua. So, we have covered Newton's second and Newton's third laws, the foundation of everything we're going to do in mechanics, which is also the foundation of everything we're going to do after mechanics. And now we're just marching through the different forces that we have in our quiver, in our toolbox. And so we're just going to explore some of those situations today and Thursday, and then in tutorials at the end of the week. Would someone be willing to give us an opening prayer to get us started off in the right way? Yes, sir. Thank you.
Father, we thank you for this day. We thank you for this opportunity we have to be able to be here in class, to be able to learn more about physics and how God created the world. And we're grateful for this opportunity we have to be able to be at this great university. We ask you to please bless us to be able to go forward with the Spirit, be able to learn, and also that people going to today that they'll be able to feel the Spirit there. And we ask you to please bless us to be able to go forward with your covenants. We say something we just grant. Amen.
Amen. At Montana State University, I would have been fired for doing that right there. This is a wonderful place. I love this place. You are great people. Okay, let's talk about apparent weight, but first let's finish up with this idea of static friction. When last we met, we too quickly, went through this old exam problem. And when this was an exam problem, it nuked the class. It just blew them out of the water. Well, for the same reason that it blew you out of the water, okay? It's tricky. And so that's what makes it a great teaching question and a really, really crummy test question, okay? This is the type of thing that you want to encounter and conquer before you get to the exam. You remember we had these two blocks, but we started out with just one of the blocks. In parts A and B, we only had block A, and it was being pulled across that rough surface in such a way that it had an acceleration of 2 meters per second every second. And we were asked about the size of the forces. Well, again, with every dynamics problem, we start with a free body diagram. And we follow the recipe. First, we put the gravitational force, the Earth pulling on the block. In this case, it would be block A instead of block B. See, that's a typo right there. I'll fix it. Okay. Then we know that the rope is pulling on A, and we know that the floor is pushing with a normal force and a friction force. That's our free body diagram. Now, every time we draw a free body diagram, we get to use Newton's second law twice, once in the y direction and once in the x direction. Since that acceleration up there is all in the x direction, none of it in the y direction, my free body diagram has to scream balance in the y direction. And that's why I put 250 here to balance that 250. Now, once I have that normal force and I have that coefficient, I can quickly find the friction force. It's the simple kind of friction, the type you can hear because there's scraping going on. And it just always, always, always satisfies that simple equation. So I take 0.3 times 250, I get 75. Now I use Newton's second law in the x direction, okay? If I take the mass of 25 kilograms and multiply by the acceleration of 2 meters per second squared, I find that I need a net or excess force of 50 newtons. That means I need 50 more newtons in the direction of acceleration than in the opposite direction. Well, what's 50 bigger than 75? Well, it would be 125. Check that your neighbor finds that trivial and is offended that I took time to go over that again. Okay?
I think that's literally it just. Yeah, yeah.
Okay. Then we got to the tricky part of this problem. We put block B back on and we pulled on the rope in such a way that we again had an acceleration of 2 meters per second squared. Now, the tension in the rope's not 125 anymore. It's got to be bigger in order to accelerate more mass at the same acceleration. Okay, but we're after something different. We're after the friction force between A and B. And we're told that the coefficient of static friction is 0.8. And indeed, it's going to be static friction because A and B are not moving relative to each other. A is moving and B is moving, but they're not moving relative to each other. There's no scraping going on between those two surfaces. And so this is static friction. Now, the first thing we're going to do is draw a free body diagram for B. And I put the gravitational force on. Now the B is correct. I then asked, are there any magnets in this problem? No. So what touches B, A, does it push or does it pull? Not a string, not a thread, not a chain, not a rope. It pushes. Whenever one thing pushes on another, it will always have a normal force. It may also have a friction force. And this is the first place that my students fell apart when this was on an exam. So many of them said, well, B's not accelerating. It's always moving with A. It never moves relative to A. Well, we don't do our physics relative to A. We do it relative to the sidewalk. And if A is speeding up at 2 meters per second every second, and if B's going with it, B is accelerating at 2 meters per second. And so I need a friction force, and it's got to point to the right. Now, some people were struggling to see why would that friction point to the right? Well, the first answer is this diagram has to screen that acceleration. And I only get one friction force. It's got to point parallel to the surface, which means either right or left. And the only way I can make this diagram screen that acceleration is to put this friction force to the right. Now, the second way to know is to use your hands, use your fingers to represent the nooks and crannies that are causing this friction. Let these fingers be the nooks and crannies of the bottom of block B. Let these be the nooks and crannies of the top of A. And then get them enmeshed with static friction. And then what you want to do is have someone pull on the rope. Hold my phone. That's an old man trick. When he pulled, try to figure out what direction is the force on the upper fingers, the ones that represent block B, and they're going to be in the direction of the pull. Okay, and so it's going to be to the right. Now, how big is it? Well, let's just use, you know the answer because we did this at the end of class last day, but let's just remind ourselves. Okay, now you can click. I don't have a problem there anymore, do I?
Here, so.
Okay, last call. Get your vote in. Okay. What happened here? There we go. Okay. You remembered the right answer was 20 Newton. Very well done. Well done. But why is that? Well, last day, the most common answer was 80 Newton because you just plugged into that formula for static friction. And here's the thing. That is not a formula for static friction. There is no formula for static friction. No formula for static friction exists. There is, however, a formula for the maximum value of static friction. That's the value at which it's going to rip free, that B is going to fall off the back of block A. 99% of the time in your homework or on the exam, you will be using Newton's second law to find the static friction. I know that this diagram on the left has to scream to the right by 20 newtons. 10 kilograms accelerating at 2 meters per second gives me a net force of 20 newtons. Well, there's only one force in the horizontal direction. It's got to be the 20 newtons.
So if the friction for B is 20 newtons to the right, is the friction for A also 20 newtons to the right?
Ah, no. What would it be? Equal but opposite. Newton's third law. If A is pushing on B 20 newtons to the right, then B is pushing on A 20 newtons to the left. Always equal and opposite by third law.
I meant A with the floor.
Oh, with the floor. Yeah, the friction force with the floor is still fighting the motion. It's still going to be to the left. Okay, because I've got the pull by the rope to the right and the friction to the left. There's more pull to the right with the tension point. Yes.
So, why is like the friction of A on B
Just like.
like A is moving to the right? Is it just because the acceleration, like you can show the acceleration on the free body diagram?
Ask that again. Why is the friction by A on B to the right? Oh, because that's what's bringing B along. That's what's causing B to stay on the back of A. If you were to grease down that surface, A would take off and B would just drop straight down to the floor. So there needs to be a force to bring B along. You let your fingers do the walking. Well, okay.
Static.
Question. Are we doing okay?
Then the next.
Don't let yourself be tricked on the exam. Use Newton's second law for 99% of the problems. I'll be right with you. What about that 1%? How do I know when to use this formula for the maximum friction? Well, that's when you look for words like, what's the biggest push you could put on this safe before it breaks free and slides? What's the greatest acceleration you could impose on A before B fell off the back? What would be the biggest acceleration that I could impose on A before it fell off the back? Yeah, 8 meters per second squared. Because if the acceleration were 8 meters per second squared, then the net force would be this maximum value here. And that means I'm right at the breaking point where the bonds between A and B are just about to fly apart. Okay. Yes, you got a question over here.
A free body diagram for A in this problem.
And the static friction.
Yes, yes. Oh, yes, all the forces that act on A in, impart, act. So let's draw that free body diagram. For A, I would still have a weight force of 250 newtons. I know that B is going to be pushing down with a normal force of 100 newtons. And so that means that the floor is going to now be pushing up on A with 350 newtons. Okay. Now, because I know that A is pushing to the right on B with 20 newtons, I'm going to have a friction force by B on A of 20 newtons here. And I'd put a tick mark here and I'd put a tick mark here, but I'd get in trouble. Okay. And then there's going to be a friction force by the floor on A, and that's going to be 0.3 times what? Is it going to be 250 or 350? Yeah, the normal force, but this is the friction between the floor and the block A. And so I want the normal force between the floor and block A. Those will always be the same indices. Okay. And so that's going to be 3.3 times 350. And then I would have the tension force by the string or the rope, I think we called it, on A.
That's your.
And I would use Newton's second law to figure out how big that was. Okay. Thank you, Sam.
Yes.
Okay.
Static friction.
Now,
Same thing.
we have a question in homework 8. This is question 6. And Greg has invented a shop dolly with frictionless wheels. Greg is using the dolly to move a large safe full of gold. The mass of the safe, including the gold, is 875 kilograms. It'll be different for you in your problem, but not by much. The mass of the shop dolly, including the wheels, is 5 kilograms. The coefficient of static friction between the safe and the dolly is large, 1.1, so that the safe does not slip relative to the dolly. Greg pushes the safe with enough force to cause it to accelerate at 0.4 meters per second every second. Find the friction force between the safe and the dolly. Now, I trust that most of you have worked this problem already and have an idea of what the answer is. Because you had different numbers, you're going to have different answers, but your answer is going to be either really, really big or medium or small. So tell me what answer was closest to what you got. Again, there's no penalty for getting a wrong answer in this class.
Last time. Yeah, no, it's 75 now.
Well, I've done happy homework, just like done that.
Okay. Tell me what you answered. You'll have a couple of more. I think that's all of us. Oh, we don't know. Okay, folks. I love this problem. This is my favorite problem in the whole textbook. This is the one that I just can hardly wait to share with you. And that's because 2 newtons is less than half of a pound. If I pushed on you with 2 newtons, you would barely feel it. You wouldn't even know I was pushing on you. On the other hand, 9,680 newtons would crush you dead. This problem is life or death. If you get the wrong answer to this problem, it's not because of round off error. It's either really, really big or really, really small. Okay, so let's work this problem together. And by together, I'm using the royal we. I'll work it on the board. Okay. So let me get some board space here. Whoever designed this room. Not impressed. Okay. Now, the first thing that I'm going to do is draw a free body diagram for everything in the problem. And since I'm looking for the friction force between the safe and the dolly, or the dolly and the safe, I'm going to draw a free body diagram for those two things, the safe and the dolly. Okay, let's do the safe first. There's going to be a gravitational force, Earth on the safe, and that's going to be 8,750 newtons. I just took the mass and multiplied by 10. I then asked, are there any magnets in this problem? No, be patient, they're coming. So what touches the safe? Well, the dolly does, and it pushes with a normal force. And it pushes with a friction force. And that's static friction, because they're not moving relative to each other. And that's going to be the dolly on the safe. And that's what I'm looking for right there. I also have this normal force by Greg on the safe. And that's my free body diagram. I'm done. So now let's do it for the dolly. I have a weight force on the dolly, and that's only 50 newtons. I'm then going to use Newton's third law to find the forces by the safe on the dolly. If the dolly's pushing up on the safe with 8,750 newtons, then the safe is pushing back on the dolly with 8,750 newtons. Okay. And does everyone see where I got that number from? There's no acceleration up or down. The acceleration is to the right, and it's 0.4 meters per second squared. Okay. So I'm going to put a tick mark here and a tick mark there. If the dolly is pushing back on the safe with the static friction force, then the safe is pushing on the dolly to the right with a static friction force. And I would put 2 tick marks there, 2 tick marks there. Finally, the floor is pushing with a normal force on the dolly. And I know that there's no acceleration up or down on that dolly. So all the force up has to balance all the force down. And so this has to be 8,800 newtons. Now you see that I've used Newton's second law in the y direction on both of those free body diagrams. So now let's do it in the x direction. For the safe, I have the normal by Greg on the safe to the right, so that's positive. I have the friction by the dolly on the safe. That's to the left, so it's negative. And that's equal to the mass of the safe, 875 kilograms, times the acceleration of 0.4 meters per second squared. And that equals 350 newtons. But you'll notice that I've got two unknowns there. I can't solve for two unknowns in one equation. So let me go to the free body diagram for the dolly. Well, for the dolly, it's really simple. I've only got one force and it's in the positive x direction. It's the static friction by the safe on the dolly. Well, by golly, that's one I'm looking for. And that's going to equal the mass of the dolly times the acceleration of the dolly. And so that's going to be 5 kilograms times 0.4 meters per second squared, or 2 newtons. Now I want you to notice some things. When I'm using Newton's second law, remember this is just F net equals ma in the x direction. When I'm using Newton's second law, the mass here is equal to the mass of what I'm drawing the free body diagram for. I don't care if there's a heavy safe on top of it. If this is a free body diagram for the dolly, just the dolly, the mass in this equation is the mass of the dolly. Okay. The other thing I want you to recognize is that 2 newtons is really, really small. And why is that? Well, it's because it's the friction force is just bringing that little tiny dolly around along for the ride. Greg is accelerating the big, massive safe full of gold, but the friction force is just bringing that dolly with the safe. And that doesn't take much. Now, if instead Greg had tied a rope to that dolly and was pulling on the rope to bring the safe along, well, now the friction is doing the acceleration of the safe, and now it's going to be a big force. Okay. Now, if we go back to this list here, I want to point out something that's a little scary. This is an old test question, and you'll notice that this is the right answer. It turns out that this is the net force on the safe. This has to be the push by Greg. This is the force you would get if you used the formula for maximum static friction with this normal force. And this is the number you would get if you use the formula for maximum static friction with this normal force. Okay. Every one of those choices represents a different way to do the problem wrong. I didn't just make up 4 numbers out of my left ear. Okay. I found different ways to work this problem wrong and made those the detractors. That should worry you. Okay. Because when you get an answer that's right there on the page, don't feel warm and fuzzy. That's not a sign. That's just a possible answer. Are there questions on this? Okay. Yes, sir.
Why is it that the static friction isn't used in this equation?
What's that?
Why is it that the static friction isn't used to find, like the static friction coefficient 1.1? Why isn't it used to find the friction between dolly?
Why didn't it use why isn't the bottom numbers?
Why didn't I say that again?
Why didn't I use the static friction equation?
Yeah, well, the one, yeah, why did you?
There is no static friction equation. There's an equation for the maximum static friction. That means the static friction could get as large as 9,625 before the safe falls off of the dolly. But we're nowhere close to that. Okay. We would have to attach a rocket to that safe to get it to.
Coefficient for static friction.
Oh, well,
Totally irrelevant. Okay. Ignore it. The important thing is that it's big enough that you're nowhere close to the maximum of static friction.
The FS, the safe dolly that you wrote on the board right there, did you also write like the net force?
I actually need it.
Yes, because there's only one force, horizontal force on the dolly, that is the net force on the dolly. It's like if you only have one bank account, we ask for your net worth. It's whatever in that bank account. Okay. Good questions, good questions. Okay. Again, I love that problem. Okay. There it is. Okay, let's turn our attention now to the gravitational force. You remember Sir Isaac Newton gave us the three laws of motion. The second one being the one we use the most, the third one being the most beautiful of all the laws of physics. He also gave us some other things. He gave us the calculus. Let's just take a moment and contemplate how wonderful that is. Just a moment of silence. That's done. That's enough. He also gave us what's called the universal law of gravity. And I think we have heard about this. A lot of us have heard about him sitting under a tree and the apple hits him on the head and suddenly he's, oh, gravity. Okay, that's as far as we usually hear about that. What we don't hear about as often is this picture that he put in his notes. And this is a reproduction of it. Newton suggested that if you went to the top of a very high mountain and fired a cannonball, it would land at the base of that mountain. And if you fired that cannonball faster, it would get further away from the base of that mountain. And if you fired it even faster, eventually the curvature of the earth is going to become important and it's going to cause that cannonball to get further than you would expect from the base of that mountain. Well, he went further and said, if you fire that cannonball really fast, fast enough, it will fall, but the curvature of the earth will cause it to keep missing the earth, and it will just keep falling around the earth, but not land, and then it will be in orbit, Now, it turns out that that speed happens to be about 8 kilometers per second, 8,000 meters per second. And that would be the escape velocity of the Earth. Okay, now let's talk about the story that we've all heard about. There's a little bit of nuance to that story. When the apple hit his head, he had this great aha. And that was that the apple is falling, but also that the moon is falling, that the moon is falling around the earth and just missing the earth like the cannonball. And then he postulated, in his mind it made sense, that the same force that was causing the apple to fall was also causing the moon to fall around the earth. Now it turns out that Galileo, remember he was the great scientist that died on the same year that Newton was born. Galileo had given us a way to calculate the acceleration of the moon. And it's easy enough to measure the acceleration of the apple. That's 9.8 meters per second squared. We can do that, okay? But Galileo gave Newton a way to find the acceleration of the moon. And we're going to talk about that on Thursday. And what he found was that the acceleration of the moon was 9.8, just like the apple, divided by 3,600. Divided by 3,600. Now, Newton knew that the moon was 60 times further away from the center of the earth than the apple. And he had created the calculus. The whole purpose of the calculus was to prove that you could pretend that the spherical earth, that all of its mass was located right at the center of the earth. Okay, that was why he did the calculus. Okay, so what he did is he recognized that the acceleration of the moon was much, much smaller by a factor of 3,600 than the acceleration of the apple. And he recognized that 3,600 was 60 squared. That's his genius there. And so he said, if the moon is 60 times further away and the acceleration is 60 squared weaker, that means that this gravitational attraction must depend on the distance between the objects squared. Okay? And this is what he came up with, Newton's universal law of gravity. And what it says is that everything with mass attracts everything else with mass. My head is attracted to that 1 kilogram. But if we tried to measure that attraction, it would be so tiny that it would be impossible to measure. Okay? But he said that any two masses, say this apple and this pear, separated by a distance r, would experience a force that was proportional to the product of the masses divided by the distance between them squared. We call this an inverse square law. And we're going to see it again in 106 next semester. Now, this is a proportionality, so we can replace the proportional symbol with an equal sign if we put in a constant of proportionality. Now, that constant of proportionality, in theory, is pretty easy to calculate. All I have to do is take one kilogram and another 1 kilogram and put them exactly 1 meter apart. And if I could measure the force between those two 1 kilograms, well, think about it. If that's 1, and that's 1, and that's 1, well, then the force is going to tell me what that constant is. All I have to do is measure that force once, and I would know what that constant was for all space and all time. But that's hard to do because that force is teeny tiny. And it took 100 years after Newton gave us this formula before we figured out what that constant was. And it's one of the most inspiring stories of all science. It was Henry Cavendish who did it. I just love this story. Henry Cavendish studied wire, all kinds of wire that were made of different metals, thick wire, thin wire. And in particular, he studied the twisting of wire, how much torque it took to twist a wire a certain number of degrees, a certain angle. And I can imagine Henry coming home to his dad one night and his dad saying, Henry, tell me again, what is it you do? Well, Dad, I study wire, all kinds of wire, and I twist the wire. Right. Get a job, Henry, get a job. Well, what Henry did with his wire is he made a great big dumbbell and he hung that dumbbell by one of his wires that he had spent his life studying. And then he brought another large boulder, a round ball nearby. And that gravitational attraction caused that wire to twist ever so slightly. But Henry had studied that wire and he knew exactly what that meant. And so he was able to calculate that value of G, 6.67 times 10 to the minus 11 newtons per meter squared per kilogram squared. Now this resonates with me because I was in grad school back east for 7 years. And we started grad school with 2 young children. We ended with 3 young children. And every year I would do unspeakable things to earn money to bring those grandchildren back to their grandparents. And every year at Christmas time, my father would say, Greg, explain to me again, what is it you do? Well, Dad, I study instabilities in inhomogeneous plasmas. Right. Get a job. Get a job. I mean, one year, a federal judge had ruled that the Army could not make our soldiers eat meals ready to eat, the MREs, unless they had a study long term on human guinea pigs. And so they took 3 healthy young males from MIT and they made them eat these meals ready for eat for 6 months, nothing else but meals ready for eat to eat. There were 3 of us that were members of the church, Shadrach, Meshach, and Abednego. And we just ate nothing but these meals ready to eat. My friend David Gibson had his sister got married in Delta, Utah during this study. He took a great big suitcase filled with meals ready to eat. The rest of the family was having a feast, and he was eating the most awful. Oh man, you got sick of them. Anyway, at the end of the 6 months, they brought all 30 of us together in a room and they said, now, we know you all cheated and we just want to know how often you cheated each week and what did you eat when you cheated most of the time. And the 3 Mormon boys looked at each other and said, what? We could cheat? No one said we could cheat. So anyway, my father was not really impressed. So let's go on with our story. What is the force between my head and a book? Well, there's my fat head in the younger time. Let's say it's 4 kilograms. And there's the textbook that we used to use that costs $250, okay? And if we put those 2 meters apart, and we use this formula here, when I plug in those numbers along with the constant that Henry Cavendish gave us, well, we get a very small number. 2 times 10 to the minus 10 newtons, 0.00000000002 newtons. Now, before we neglect that and throw it away, let's answer this question. Is that going to be the force by the head on the book or the force by the book on the head? Or do I have to cut that in half and give half here, half there? Which is it? It's both. You can see that Newton's 3rd law is built right into Newton's law of gravity. Okay, 3 times 4 is equal to 4 times 3. You're going to get the same answer either way. Now, let's just agree that the only time we're going to worry about gravitational forces is when one of those objects is very, very large, like the Earth. Now, if I wanted to find the gravitational force between the Earth and that book, well, we already know how to do that the quick and dirty way. You take the mass of the book and you just say that the Earth pulls with 9.8 newtons for each kilogram. So if I've got 2 kilograms here, I multiply that by 2 and I get my gravitational force. But Newton said we could also use this universal law of gravity. So in order to do that, I need to know some things. I need to know the radius of the Earth, but that's simple. When I was teaching high school teachers during the summer, I would have them calculate the radius of the Earth just by using a meter stick and a duck pond that was on campus. Oh, and Mount Rainier on a clear day when they could see it. And they would sight along the duck pond to where the top of Mount Rainier was, and they would use similar triangles to figure out how far away Mount Rainier was. And of course, their answer would be different than the real answer because of the curvature of the Earth. And then they could simply figure out the radius of the Earth. And they could do that back in their day as well. And so I also need to know the mass of the Earth. Now that's harder. That's harder. How do you find the mass of the Earth? Someone's got to shake the Earth, right? Who's going to do that? Volunteers? Okay. Put it on the big old scale. Okay, but you see that if I use this formula with that constant that Henry Cavendish gave us, we're going to get the same answer that we got the easy way. What that means is that everything in this red box has to multiply and divide out to 9.8. Now think of what that means. As soon as Henry Cavendish figured out this number here, he knew what the mass of the earth was. And so I can imagine Henry coming back to his father and saying, Henry, what is it that you do? Well, Dad, today I figured out that the mass of the earth is 6 times 10 to the 24th kilograms. Until today, no one knew that. And now, only me and you, Dad, just me and you, that know that answer. I love you, Dad. I love that story. I made it up. Okay. But I think that's the way it went. I think that's the way it went. Okay. Who's that? Anyone know? No, it's not John Glenn. It's Story Musgrave. And you probably didn't know that his mass was 80 kilograms, but I'll let you know that. Okay. Here's another picture of Story Musgrave floating next to the space shuttle. And if I ask you, what's his mass? What's the answer? 80 kilograms. That stays the same wherever you go in the universe. That's how hard it is to shake something. But what's his weight as he floats there? What's his weight? Okay. His weight, it turns out, is 648 newtons. What? He's weightless, Greg. It said so in the newspaper. The newspaper wouldn't lie. I saw it on the TV, on the intertube. No, he is not weightless. His weight is 648 newtons. How did I get that number? Well, there's the Earth as seen from the moon. And if your parents taught you we never went there, then just ignore this part. Which of those circles represents the orbit of the space shuttle? What do you think? Yeah, the white one. They don't go very far from home. Back in Bozeman, where I used to teach, we had a member of our faculty that was a mission specialist on the space shuttle. And I asked him, I said, Lauren, how high did you go? He says, oh, we aren't that high. We're just 400. Let's go back. We're just 400 miles above the surface of the Earth. So if we take Story Musgrave and we put him in his bathroom and we use the gravitational field strength on Earth, he's going to have a weight of 784 newtons. But if he's up in the space shuttle, 400 miles above the surface, well, that's just an extra 10% away from the center of the Earth. The gravitational field strength is going to be weaker than 9.8, but not a whole lot weaker. It's going to be 8.1 instead of 9.8. And that's where I got the 648 newtons. Now he appears weightless. And so we're going to define a concept that we call apparent weight. And we would say that Story Musgrave's true weight, the gravitational force exerted by the Earth, is 648 newtons. But his apparent weight is zero. Now, that may be confusing. Let me see if I can make it less confusing. I have here a bathroom scale. And if I stand on that, oh my. Okay. Used to be worse. Okay. The question I have for you is what force is that bathroom scale measuring? If I draw a free body diagram for the Greg and for the scale, there are 5 forces on those diagrams. And I want to know which of those 5 forces does the scale read? Which one of the five forces does the scale read? Talk to your neighbor. See if your neighbor can figure it out.
Which seems to be other two.
I don't know.
Okay, I'll give you a hint. The scale can only read a force on the scale. So it has to be one of these three on the right. And the one that it's going to be is the push by the person on the scale. How hard you push on that is what the scale reads. Now, by Newton's third law, that has to be the same as this force by the scale up on the person. And if this whole thing is stationary, if there's no acceleration, you're standing in your bathroom, then by Newton's second law, you're indirectly measuring your true weight, the gravitational pull on you. Now, this we call the apparent weight. This we call the true weight. This gravitational force, non-contact force, the weight force, can only be changed through diet and exercise. But the contact force, the push by me on that scale, I can make that anything I want, okay? By accelerating. Now, let's talk about the apparent weight. It's measured as the reading on the scale. It's equal to the normal force of the scale on your feet or whatever's keeping you from free fall. And it's equal to the weight in the special case of zero acceleration. In the special case of zero acceleration. Okay? Now, let's look at the case where you're in an elevator. If that elevator has zero acceleration, let's say it's going up to the 10th floor at a constant 20 meters per second. It's a really fast elevator, but it's a constant 20 meters per second. Zero acceleration. It doesn't feel any different than being in your living room. And if I draw a free body diagram for the Greg, this weight force, let's be generous and say that's 200 pounds. Okay. This diagram has to scream this acceleration. So the normal force, how heavy I feel, is going to be 200 pounds. The apparent weight would be the same size as the true weight. But if I have an acceleration up, and remember, this could either be moving up to the 10th floor and speeding up, or moving down to the lobby and slowing down. If I have an acceleration up, my true weight is still going to be 200 pounds. But my diagram has to scream this acceleration. And so that means I'm going to feel much heavier than 200 pounds. I'm going to feel like I ate 6 Big Macs, okay? Because the floor is going to feel like it's pushed up into my feet, pushing my feet up into my head, okay? Does that make sense? I feel much heavier. My apparent weight, I would say, would be greater than my true weight. If my acceleration is down, like you're on the 10th floor and you hit the button for the lobby, and suddenly the floor falls out from under you, okay? Well, in that case, my true weight is still 200 pounds, but my diagram has to scream this acceleration. So the push by the floor or by the scale has to be much less. It feels like I'm light on my feet. This diet's working until I get to the lobby.
So the true weight always stays the same?
The true weight always stays the same unless you diet or exercise. Okay, that's the good news. Okay, there is a way to change the true weight.
Be like in a cell.
Oh, you can also go to a different planet. Yes.
So with the elevator, you basically just like never mind my question.
Okay. He knows your question.
With the elevator, when do we know when the acceleration's up versus down?
Oh, if it's speeding up, the acceleration is in the same direction as your motion. If it's slowing down, it's in the opposite direction of your motion. Everything we learned earlier in the before times still true. Okay? Good? Everyone good? Now, let's do this problem here. You're riding down in an elevator carrying a 20-kilogram package in your arm. As the elevator gets to your floor, it slows with an acceleration of 2 meters per second per second. What is the apparent weight of the package? How heavy does it feel while the elevator is slowing? This is the type of problem you will need to solve on the exam. Okay, so let's do it together. Sam, could you help me real quick? Get some space. Thank you. I just need that center one. Okay. So if I draw a free body diagram for the U, okay, I've got a gravitational force on the U. I have well, you know what? Let's not do the free body diagram for the U. Let's do a free body diagram of the simplest object, the package. I have a gravitational force, Earth, on the package. And that's just going to be, it's a 20-kilogram package times the gravitational field strength of 10 newtons for each kilogram. That's going to be 200 newtons. Everyone see how I got that? Okay. The only thing touching the package is you, and you're pushing with a normal force. And if you're moving down and slowing down, your acceleration has to be opposite your velocity, or up. And we're told that it's 2 meters per second squared. And so that means this diagram has to scream up. I've got to have more force up than down. Well, how loud does it scream? Well, the answer to that is always given by Newton's second law. F net is the scream. And I want to take 20 kilograms and multiply it by 2 meters per second squared up. And that's going to give me a scream of 40 newtons up. And so that means that this normal force has to be 240 newtons. And this would be the apparent weight. And this would be the true weight. Now, I want you to notice something. There is no formula for apparent weight. You just use Newton's second law. You just use Newton's second law. Okay, there's not a separate formula. Check that your neighbor's on the bus, people. Do a buddy check.
I'm interested.
But if you were going up.
Okay,
Yeah.
now, if the stream method doesn't work for you, just expand out the net force. If I'm calling up the positive y direction and down the negative y direction, I've got the normal force by u on the package, and it's up so it's positive. I've got the 200 Newton weight force, it's down so it's negative. That's going to equal the mass of 20 kilograms times the acceleration of 2 meters per second squared. It's up so it's positive. And then you solve for n, you get 240. Okay, you can just plug and chug into F net equals ma. Okay, let's places to go, people to see. what if in that elevator, I have a special value of my acceleration down, namely 9.8 meters per second per second. And it's easy enough to create that situation. You just cut the cable, okay? That's free fall. And if I look at the three body diagram, Greg still weighs 200 pounds, but how big does that normal force have to be for free fall? 0. And so watch, this is clever. Watch, watch, watch. Pow. Pow. Okay, yeah, let's do it again. Pow. Now he's floating. Is he weightless, I ask? No, his weight force is going to kill him in just about a half second, okay? He's apparently weightless. He's apparently weightless. He's floating around, he's falling, the elevator's falling, they're all falling together, and he appears to be weightless. Now, you've all seen this movie, Apollo 13, and in that movie, let's see if we've got our sound up on this thing. We do not. Okay, I'm gonna turn off the lights. You don't have to go to sleep, but again, you can. Okay, how did they film that? Do they have a special room in Hollywood where they just flip a switch and turn off gravity? No, they did that in what's called the vomit comet. Okay, and what that does is the pilot just goes up really steep and then puts the plane into a dive. I've got a video of some students from MSU. Too much information. Okay, BYU students have also done this.
The students through a week-long training to prepare them for the flight aboard the vomit comet, named because of the number who become ill while swirling and twisting in midair. They start to float, they start to drift. And it takes them up to about 25,000 feet and then goes into a steep dive. At a certain point, the passengers start falling at the same rate as the plane and gravity disappears.
Okay, now think of that cannonball that Newton told us about in his notes that was falling around the Earth and always missing it. Well, that's what the space shuttle was doing. It was falling around the Earth and always missing it in orbit. And so just like falling in an elevator, falling around the Earth next to the space shuttle, you appear weightless. You appear weightless. Okay. These are some slides from Dr. Benyon, who teaches the afternoon class. He shared them with me this morning. Newton's secret, what is the most typical date at BYU? Dinner and a movie. Why? Why dinner? Okay, well, that's because more mass, greater attraction. Why a movie? Well, at the movie, you sit right next to each other, smaller distance, greater attraction. Okay, Is that corny or what? I'll tell him. Okay, I'll tell him. We're gonna talk about one more quick idea before we disband. And I'm gonna start with this cartoon, Funky Winkerbean. A lot of the other school bus drivers complain about kids fighting and fooling around on the bus. Hooey, I never have any trouble. If you go fast enough, they just say pin to their seats. Now, all of America laughed at that cartoon when it came out many years ago, but I suspect that some of them were not laughing for the right reason. How do you pin those kids to their seat? Yeah, with high acceleration. If you're going very, very fast with zero acceleration, they don't know that they're not in their living room. Okay. Now, when I say I have lost my equilibrium, what that means is I have lost my balance. Now, there's a whole host of problems that we call equilibrium problems. And those are problems in which the forces acting on the object are balanced. Or I could say those are problems in which the object has zero acceleration. And I hope that you see by Newton's second law that those are the same. If there's zero acceleration, there has to be a balance in the forces. The free body diagram has to screen balance in both the x direction and the y direction. Now, is this equilibrium? A rocket ship has lost all of its thrusters and is now hurling helplessly out into deep space at a velocity of 5,000 meters per second. Is this rocket in equilibrium? Yes or heck yes? Yeah, it is. The velocity never matters. It's the acceleration that matters. The acceleration matters. Here's another problem that we've encountered before in the homework. Jeff, my friend, is trying in vain to push a large freezer of elk meat, this is a Montana problem, across his garage floor. The mass of the freezer, including contents, is 250 kilograms. The coefficient of static friction between the freezer and the floor is 0.8. Jeff is pushing with a horizontal force of 1,000 newtons, but the freezer will not budge. What is the magnitude of the frictional force acting on the freezer? And you get these two formulas here. Tell your neighbor the answer real quick. Tell your neighbor the answer. Okay. It seems like a trick question. The answer is 1,000 newtons. He pushes one way on the fridge and it does with 1,000 newtons and it doesn't budge. The force that's balancing the free body diagram is the friction force, the static friction force. If he pushed with 1,200 newtons, the static friction would be 1,200 newtons. It's not until he pushes with enough force to break that free, 2,000 newtons, I believe it is, would cause that to break free. But we're nowhere close to that breaking point. Okay. So what do you do with this formula for static friction? I just tricked you. There is no formula for static friction. It doesn't exist. It's a formula for the maximum static friction. And what you do is you ignore it. You ignore it. Okay. Now, last week, last day actually, we had this pretest, and you were asked to draw free body diagrams for the rock and the crate. Now, I've told you to always draw the simplest free body diagram first, the object that's touching the fewest other things. That's the rock. So I put the weight force, always first the weight force. Then I ask what touches the rock, the crate. Does it push or does it pull? It pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Is there one in this case? Tell your neighbor. Is there one in this case?
There's all
Okay. Remember, we're told that it moves at constant velocity. So there is no friction force. Okay, it's a rough rock. It's a rough crate. There's lots of nooks and crannies. But this diagram has to scream balance, has to scream zero. And I only get one friction force, and it either points to the right or to the left if it's there. I don't want this diagram to scream to the right. I don't want it to scream to the left. Well, how can that be if there's nooks and crannies, Greg? Well, let's grease down that crate and grease down the bottom of the rock. And let's start from rest, shall we? If I push on that crate from rest, I'm going to push the crate right out from under the rock. The rock's going to fall and break my foot, right? But if while I push to speed up the crate, I also put my hand up to push the rock, and I get them sped up to the same speed, the same constant velocity. At that point, I can take my hand off the rock and it'll keep going. Something in motion wants to keep in motion at the same velocity. And so even though there's nooks and crannies that are intermeshed with each other, they're not pushing on each other because the rock wants to go the same speed that the crate is going. See if your neighbor followed that, please. See if your neighbor followed that.
Not accelerated. Guys pushing.
Okay, let's finish our free body diagram. The earth is pulling down on the crate, and if the crate is pushing up on the rock, then the rock has to push back on the crate. And then the floor is pushing up on the crate. There's friction by the floor on the crate. And for constant velocity, you've got to push just as big as that friction force. Now, the third law companions, I've got the two normal forces, crate on the rock and rock on the crate. What about the weight force, earth on the rock? Well, that's also going to be a gravitational force, rock pulling on the earth, and I would put 2 tick marks there. Now be careful on the next exam, because there's 2 ways I can ask about third law pairs. One way is to say, if you've got any third law pairs on your diagrams, mark them with tick marks, in which case you just have to mark the normal forces. The other way to ask it is, for each and every force on the rock, tell me what the third law companion is. If that's the way I ask the question, and you only mark the normal forces, you'd get half credit, okay? Don't let that be you. Turn to your neighbor and say, that's going to be you, not me. Okay.
He looks like multiple.
You know what? This is a good place to stop, people. You have a great day. There's a devotional over in the Wilkes, no, not the Wilkes, the Marriott Center. The bigger Wilkes.
Probably was more than that.